All right, and welcome back to your notes. So we just figured out how to find the least squares regression line using our calculator. It's our stat button and then calc tab, option 4. And then we got that y hat, that A on the screen was this, and the B on the screen was this. All right, and there you go. Okay, and now we want to predict the drilling time if drilling starts at 100 feet, or excuse me, 130 feet. All right, so predict means we're going to plug this in to our formula. If the drilling starts at this feet, this is a value of x. So we're going to plug it into our formula. Okay, and if we work our calculator magic, we get, we get this. All right, so again, I'll remind you how many decimal places to round to in your quiz or exam, and your homework tells you. Please remember that we are dealing with units. Predict the drilling time. So this is 7.0353, and then it's in terms of minutes. So you see the minutes right there. Explanatory variables in terms of minutes. So we're going to want to make sure we throw in the minutes. And remember, this is an average. So it doesn't ask us to interpret this, but if we wanted to interpret it, we could say something like on average. Okay, so if I'm asking you to interpret it, I'm going to be looking for this phrase on average. So I know that you know y hat is an average. If the drilling time starts at 130 feet, if the drilling time starts at 130 feet, drilling starts at 130 feet. And now I'm going to state our variable, the time to drill 5 feet, will be 7.0353 minutes. And you can either write average at the beginning, or you can write on average at the end. Just make sure you include on average, because y hat is an average, and I want to make sure you know that. All right, and again, that's the red part. Predict the drilling time if it starts at 130 feet, and then what I just wrote in red would be like the interpret part if I asked you to interpret. Okay, so let's go down to this next part. We want to know, is the observed drilling time at 130 feet above or below average? So observed means we're going back to our table. These are the observations, right? These are the observations. So at 130 feet, in this case, it was 6.93. 6.93. So, and remember, the average is 7.0353. So we want to know how the observed time compares to the average time. So let's write it out. The observed time is 6.93. The average time is 7.0353. So which one's bigger? The average is bigger. So the observation is below average because the observed time is less than the average. So we are below average. All right, and then now that we also have the observed and the predicted value, we can look at the residual. So this is kind of a bonus round, but you're going to see this question pop up in your homework and then possibly on quizzes and exams. But the residual, remember it's the observation minus the prediction. And because it's below average, it means it's beneath the line, and so we would expect to have a negative residual, and we do. The residual is negative 0.11. All right, and then drawing the least squares regression line on the scattered diagram of the data, you guys can sketch in part D into the scattered diagram. You can also take what we did in part A, this line, and then graph the scattered diagram like we did in section 4.1 on your calculator, and then put this line in your y equals button. So instead of going to second stat plot, you can plug in part A into y equals on your calculator and hit graph. And that will show the least squares regression line on the scattered diagram. All right, let's look at another example. And I'll have you guys plug in this information into your calculator. So this says the given data represents the interest rate a bank would offer on a 36-month auto loan for various FICO scores. And so how loans normally work, if you have a good credit score, your interest rate is lower. If you have a bad credit score, your interest rate is higher. All right, so it seems like that's a negative association. So find the least squares regression line. So you guys will be doing this on your calculator. Your credit score is your explanatory variable, so you'll put that in list 1. The interest rate is the response variable, so you'll put that into list 2. And then you'll hit your stat button, you'll go over to calc, and you'll hit option 4. And then your least squares regression line is going to be this. So make sure we're comfortable with our calculator function and all of our numbers match up. All right, and let's see what this problem is asking us. So part B says Bob has a FICO score of 680 and is offered an interest rate of 8.3%. Is this a good offer, and why? Well, let's use our least squares regression line to see what the average interest rate would be. If this is above average, that's a bad offer. We don't like high interest rates. But if it's below average, that's a good offer because it's a lower interest rate. So to determine if it's a good offer, we'd have to know the average offer. All right, and y-hat predicts averages. So we have our least squares regression line, and the value of the explanatory variable is 680. And so the average interest rate at that credit score is this. All right, so again, remember this is the average interest rate as a percentage. Okay, so what are we going to look at this 8.3%? Is it above average or below average? It's below. So 8.3% is below average for that given credit card score. So we can conclude it's a good offer. Because it's below average. Okay, and then part C, we're going into the interpretation of the slope and the y-intercept. Before we do that, let's explain how we're going to interpret the slope and y-intercept. So we'll come back to this page. All right, and then we're going to head on over to the interpretation of the slope and the y-intercept. Okay, so this is the least squares regression line for our drilling 5 feet at various depths. So we did that in our first example. And we know all lines have this format, y equals mx plus b. So in our case, our slope for this line is 0.016, and the y-intercept is 5.5273. So let's write that in. I'm going to make this a little bit bigger. So m is 0.0116, and our y-intercept is this. Remember, y-intercept happens when x equals 0. So in this case, the y-intercept happens when the explanatory variable is 0. Okay, so let's start with interpreting the slope. Remember that the slope is the average rate of change. So it's delta y over delta x. We did that at the very beginning of this section. So delta y, we can think of that as the change in the response variable, because y are the response values. And delta x, it's the change of the explanatory variable. Okay, so let's interpret the slope. So I like to do it because this can get a little intense if we're not careful, we're not keeping track of everything. So I like to break it down because when we interpret the slope, we have to include the units of the slope and write the interpretation using complete sentences. So I like to do a little bit of mental work. So number 1 is my mental work. I like to write the units of the slope. So in our example with the drilling depth and drilling time, the drilling time was measured in minutes and the drilling depth was measured in feet. So those are the units. Okay, so in our case it's minute per feet. All right, so that's what I keep in mind, and then I have my actual interpretation. So number 2 would be your answer. All right, so this is saying minute per foot. So per foot, it means when we increase by 1 feet, the drilling time goes up however many minutes that the slope is. So let's write that out. For every additional, or for each foot increase of drilling depth, or starting depth, I should say, all right, so we're going up 1 unit of our denominator. The time to drill 5 feet, that's our response variable. And then again, just let's reference our slope. It's 0.0116. It's positive, so we're increasing. So we can write increases because the slope is positive. And it increases by the slope many minutes. Okay, so that's interpreting the slope. That's actually something we've seen, or maybe we've practiced in an algebra class. We also have to include on average, because y hat predicts averages, right? So on average, make sure we don't forget that. All right, so just some like a checklist we need when we're writing our interpretation. Make sure we have our units. Make sure you include the slope, right, which is right there in this case. You want to name out your variables. So we have our variables foot increase of starting depth and time to drill 5 feet. Those are both of our variables. And then you want to include on average. Okay, so a lot to remember in this interpretation. Okay, so let's go over how we're going to interpret the y variable, or excuse me, the y-intercept. And we already kind of talked about it. We saw that the y-intercept happens when the explanatory variable is 0. So we have to make sure of a couple things when we're interpreting the y-intercept. Does it make sense for the explanatory variable to be 0? And is the value of 0, x equals 0, somewhat close to our data set? Okay, so let's write that out. So to interpret the y-intercept, again, that's when the explanatory variable is 0. We need to ask ourselves two questions. We're going to ask ourselves, self, is 0 a reasonable value? For the explanatory variable, and we ask ourselves, self, do any observations exist relatively close to 0? So if we answer no to either of these questions, it doesn't make sense to interpret the y-intercept, and we don't do it. Okay, so this is our example. So if we want to interpret the y-intercept, we'd ask ourselves, does x equals 0 make sense? So that's a drilling depth of 0 feet. Can we have a drilling depth of 0 feet? Well, yeah, it just means we're starting to drill on the surface. So it makes sense. So let's continue. Do we have observations relatively close to 0? All right, and if you look back on our data set ranges from 35 to 190, so like 35 to almost 200. So in this case, I would say that's relatively close to 0, just given the span of our data. So we'll just say yes. Okay, so in that case, we are able to interpret the y-intercept and that y-intercept, come on, is 5.5273. And again, it's a y value. When our x is 0, x equals 0 is the explanatory variable. And so it's not 0, it's really 0 feet. The y-intercept is not just 5.5273, it's 5.5273 minutes. So it's the time it takes to drill 5 feet at the surface. Okay, so that's pretty much your interpretation. We would have to write out a complete sentence just as before. So we could say at 0 feet, or we can interpret it even farther. We could say at the surface, it will take 5.5273 minutes to drill 5 feet. And then because it's y hat, which predicts averages, we would have to say on average. All right, so make sure you don't forget that on average part. All right, so let's head back up to the example with the credit card scores, with the corresponding interest rates, and we're going to now interpret the slope and the y-intercept. So remember, our slope was, we'll start with the slope. Your slope was negative 0.0764. So to interpret the slope, again, first I like to think of the units. Response over explanatory, interest rate over credit score, points. Scores are in terms of points. So it's percentage per point, and right? So it's actually negative 0.0764% per point increase. All right, and essentially that's what our interpretation is. Our actual answer, again, is part 2. We would say for each additional credit score point, or for a point increase, something like that, the interest rate will, all right, and because we have a negative slope, we're going to say will decrease, because it's a negative slope, decrease, we can drop that negative sign now, 0.0764%. And then, of course, we need on average. All right, and there you go. Okay, so let's look at part 2, the y-intercept. We're going to interpret the y-intercept. So let's interpret it first, and then we'll see if it actually makes sense. So again, y-intercept, when x equals 0, the y-intercept in this case was 61.3687. So the 0 is the explanatory variable, so your credit score is 0. And then this is your response variable, so it's your interest rate. So this is really a percentage. So the interpretation is we would say for a credit score of 0, you could say the average interest rate, or you could say the interest rate is 61.3687% on average. Just make sure you throw in the word average somewhere. On average. All right, but is there such thing as a credit score of 0? No, The lowest you can be, if you look at the top of your page, it says the range of the credit scores, and the range is 300 to 850. So the lowest credit score is 300. Not 0. So 0 doesn't make sense. We don't actually interpret the y-intercept. Or we can just say, so no interpretation. No interpretation is needed, but I still want to see it. And then we can just make a note on a quiz or an exam. Actually do the interpretation, but then we can just say the interpretation doesn't make sense, or we don't actually need it. Something like that. All right, so there's our interpretation of the slope and the y-intercept. We have one more thing to cover in this note packet, in this section. Let's go all the way down. And this is just saying, and we kind of touched on it in the y-intercept interpretation, we want our predicted values to be close to the actual observations. So that's this part right here. Whenever we use y-hat to predict the values of response variables, we need the values of the explanatory variable to be close to the data set. Otherwise, we risk working outside the scope of the model. Okay, so our least squares regression line is only guaranteed for values that are close to the actual observations. So to briefly illustrate this, let's take our drilling depth example in feet and the time to drill 5 feet in minutes. All right, and then we had all of our observations, like let's say we had them all right here. Okay, so we only went down to like 200 feet. But we know that we could dig much, much deeper, right? So let's say this is our least squares regression line. And we wouldn't want to use this to, let's say, predict what would happen at like 1,000,000 feet. Okay, so somewhere up here, because at some point we will hit the center of the earth. So this is, your y-hat, your least squares regression line, but it might only be relevant, let's say, to maybe right there. And then as we're going closer and closer to the center of the earth, well, it's going to start getting pretty hot, right? And as it gets hot, our rock is going to be melting, and then we have our molten lava. And now the time to drill 5 feet, well, there's nothing to drill, right? If it's all melted, everything is just even the drill will melt, right? So this is a very confusing situation. So the point is, at some point, we're not going to be able to use our least squares regression line. So we have to make sure whatever we're predicting, the explanatory values that we're trying to find an average for, it has to be close to the observations.